Okay, so we're ready to go. Where's our chart here? Okay, so today it's a first lecture which starts really digging into operating systems. And our goal today is to understand the interface of the operating system. So essentially, remember we talked a little bit about it last time during the introduction. We said that operating system can be viewed as a library which provides a collection of services, right? And today we want to understand what these services are, and we'll try to understand essentially a collection of system calls which operating system kernel provides, right? And we go through them one by one, and the beauty of this operating system, which is called x86, right, which we're using in this class, is that all the system calls they fit on one screen. That there are like roughly 15 of them. And nevertheless, they're powerful enough. So this is the original Unix interface, and it's powerful enough so you can still run most of the functionality which you are running today. Although today the number of system calls is roughly around 200, but they're just like added for different purposes, right? Okay, so just a quick recap of what was happening last time. So although we skipped most of the introduction, right? So let me just quickly tell you that what's going on. So remember what we said, that the operating system can be viewed as a piece of software, which essentially which essentially is the first thing which boots on the machine, right? So I remember we had this example of maybe a simple Fitbit device which you are trying to develop, and some piece of code which boots on the hardware becomes an operating system, or we can call it also a kernel. And this kernel provides some interface to the processes which it runs on top. So it essentially starts multiple processes. Maybe this is a shell. Maybe this is something like your word processor, I don't know, maybe a Vim editor, or maybe Visual Studio Code. Maybe this is your web browser, right? And what operating system enforces is that it allows these individual processes to take turns on the CPU. So essentially, process 1 runs for a while, then process 2 runs for a while, then process 3 runs for a while, and then it turns and again runs P1 for a while again. So they take turns, right? And this sharing and multiplexing of hardware is one of the functions which operating system provides, right? Another function which it provides, it's that it abstracts low-level details of hardware, right? So essentially, if you have an actual device, like maybe a 10 Gbps network interface, right? So you can get a data sheet and for this specific device, and implement code which allows you to send and receive packets, right? And this piece of code will be called a device driver. It will be running as part of the operating system kernel. But really, for you as the user of this process, you don't really care about this datasheet. You don't even care which device you're using, right? Because your program, this web browser, is supposed to run on any of the platform, no matter which physical hardware it has, as long as it is a network interface, you should be good, right? And so operating system provides layers of abstractions. One, like device driver, exports a slightly higher level interface to the network stack, and then there is a collection of network stack protocols. And in the end, your process talks to the operating system saying, okay, here's a stream of data, which is accessible through something what is called a socket. And I can write it into this stream, and magically this data appears on the other side of the world when it traverses like the global networks, like an internet, right? And that's the essentially layering of those abstractions. And we also briefly talked about it last time. And so you can view as well operating system as a library which provides a collection of services, right? So you have interfaces to read and write files, you have interfaces to read and write, to send and receive network packets, right? And also operating system provides isolation between processes. So essentially, if you're running multiple processes on the system, there is kind of like an isolation boundary, which ensures that one process cannot access memory of another process. This is not allowed, right? And this is pretty much intuitive, right? So sorry, if someone would ask you, would say like, yeah, my web browser in which I'm running like some suspicious websites shall not be able to access another web browser tab, which maybe in which I opened my bank account. So these days, typically those individual tabs run as individual processes, which are isolated by the operating system, right? And also a process cannot access memory of the kernel, right? So that's pretty much kind of like intuitive understanding of what operating system is doing. So let me stop here again for questions. Do you understand this high level view, at least intuitively? And I forgot, guys, did I enable recording or did I forget? Pause recording. So it looks like it's running, right? Can someone confirm that you get us?
Yeah, it's running. It's running.
You got it. Thank you. Okay, sorry, because the deal is that I cannot automatically enable recordings. Like I did it once, but it turns out that I first have to share my screen and then enable recording. And then Zoom on Linux feels like everything is good. But if you don't do this, then Zoom is upset for whatever reason and everything becomes horrible. Okay, so back to slide number 2. Sorry about it. Come on. Now Zoom and LibreOffice are upset at each other, I guess. Okay, so if we take a look, and you will see this picture over and over in this class, right? So it will be like it become familiar to you. That piece of that's the architecture of a modern commodity operating system. There are different research directions which explore different research, which explore different architectures, possible architectures of operating systems. But this is de facto standard which you are running when you run your Windows machine or run your Linux machine, and even macOS. Or the macOS has a microkernel underneath, right? But what's happening here is the following. So this piece, which is yellow piece, and I will be always using yellow color for the kernel. And kernel, it's operating system kernel. So it's kind of a slang which essentially names this piece of software which boots on the hardware and provides operating system services. And if you look inside here, you will recognize familiar pieces, right? So you have a file system which allows you to read and write files. You have a scheduler which allows you to pick, which doesn't allow you, but which like essentially makes sure that each process in a system has a fair fraction of a CPU, right? Maybe according to its priority. There is a network stack, which allows you to send and receive packets. There is virtual memory, which makes sure that, each process gets a different set of pages, and then, it supports allocation and deallocation of virtual memory regions. I don't have device drivers, but probably I should add and say that, okay, those are device drivers here as well. And on top of that, we have processes which are running at a different privilege level. So we're going to talk about privilege levels later on. But roughly speaking, the intuition here is the kernel which boots on the hardware runs at the most privileged level, which is level 0. And user, or we can call it ring 0, and user programs run at ring 3, which is the least privileged level, and which allows us to ensure that the applications cannot really access memory of the kernel, cannot access memory of other processes, and also cannot invoke any of the sensitive instructions which can break this isolation, which essentially operating system kernel establishes, right, through page tables and other isolation mechanisms, right? But so imagine you're running shell here, imagine you're running Apache server here, and now the question, and this is the topic of our lecture today, is this operating system call interface, right? The idea is that, remember I told you that operating system is like a library. So if you want to access a function of a file system, kind of like open a file. So what you do here, you write something like open, provide a file name like /foo, txt, for example, some maybe flags, read-only and stuff. What happens next is that really not the libraries here execute this functionality of open, but instead they just invoke something what is called a syscall or a system call, right? And this invocation is passed in a secure manner to the operating system kernel. And at this point, it reaches file system and really this is the part of the system which implements something with like sysopen, right? So the functionality of the open system call, right? So essentially the system library, which typically on Linux it's libc, and I don't know what it is on on Windows. Maybe it's something like Win32DLL, and whoever codes on Windows can correct me, because I used to know, but now I'm no longer remember, and I don't no longer remember what it is, right? So, and today's lecture is about what this interface should be. Imagine we want to build an operating system kernel, and imagine we're designing from scratch. The question is like, what shall it be, right? What kind of functionality the operating system interface should provide to the applications that you can do all what you want, right? So like support all the flexibility of like running whatever you want on this machine. Okay, so before getting there, just a slight detour. I mentioned system calls, and you probably have heard these words before, right? And probably not many people really know how they work, like what is the machinery which is involved in the invocation of a system call. Well, first of all, let's understand the following. So why can't we just invoke a function, right? One can say, okay, we can probably invoke a function. So if it's the open, why not to simply have this open function here, which implements this system call? The answer is this isolation, right? So this boundary which is running here, it ensures that the user level program cannot really access memory of the operating system. So they run at different privilege levels. An attempt to access a memory location, which is somewhere in the kernel, will trigger a page fault in a modern operating system. Although like in a different setup, it can be a segmentation violation, segmentation fault, or can be something else, depending on the isolation mechanism. But let's just say it's a page fault, like in x86. And that's why you cannot really just simply invoke a function, right? Because isolation with functions doesn't work. It works in safe languages, like if you write the entire stack in a safe language, so for example, in a safe subset of a Rust language, or maybe in a subset of Java, and like whatever is your favorite safe language, you can enforce this isolation at the level of language. But typically that didn't become mainstream, and today we run unsafe languages like C, which enforce no isolation with the language, but instead like rely on these hardware primitives like page tables plus segmentation to enforce this isolation. And okay, right now, you don't have to really understand it. It's just a detour. We will spend like one or even 1.5 lectures discussing in details. First, one lecture on segmentation and paging, maybe 2 most likely. And there will be a second lecture, a separate lecture on invocation of system calls. So don't worry about it, but just a heads up, the way it works. So instead of invoking something like an assembly call function, which invokes open and jumping here, the user level library, this libc, invokes something what is called an int instruction, triggering an interrupt with a specific number. And then control goes, remember we were talking about this fetch, decode, execute loop, and there was a condition that there was no exception. So this instruction actually triggers an exception, and control goes to an interrupt descriptor table. Hardware looks at the handler, which is placed there by the operating system. It's like a vector, essentially a handler to handle interrupt x80, jumps here and essentially starts executing in the kernel, because this interrupt transition triggers the privilege level change from ring 3 into ring 0. And then eventually it reaches this sysopen implementation in the kernel. But think of it as a kind of a checkpoint, security checkpoint at the airport, in which you say, look, we know that you can only enter through these gates, and this is the gate on this interrupt descriptor table entry, right? So an operating system is configuring this gate, and this gate will very carefully check all the arguments which are passed inside to avoid various security attacks on the kernel, right? But again, today it's not the subject. Today the subject is simply to understand what kind of interface it should be, right? And here, let me stop and ask you, so what system calls do we need really, if I ask you? So can someone name me a couple? Read and write. So, and file IO, I agree with you. So we want to access files, file IO. So those will be like open, read, write, and close, right? There is a couple of others, like if you're careful enough, you can think of, okay, we need to be able to change directory, meaning that, you know, typically your path is relative to the current directory. So change directory, and you also need to be able to create new directories, right? Because in a file system, right? But in general, you're right. So it's file IO. Then someone says memory access, meaning that allocation and deallocation of memory. And at the level of the system call interface, there is just one system call, which is called SBRK, which essentially extends memory of a process. So if the memory of a process was such as BRK, you pass an argument and you say, like, add me a little bit more data, a little bit more memory, right? Or decrease my allocation, at least in x86, and that's good enough. Yeah. Then someone says hardware access, network GPU. So GPU is a little bit tricky, but again, even the GPU is accessed through layers of abstraction. So you then don't get access to the real GPU hardware. So it's similar to files and network. If files, and here on the left side is what is present is an x86, and x86 doesn't have network interfaces. So sockets here are not in x86, but you write that send and receive through a socket, opening a socket, binding. This is the layer to access the network interfaces, right? But through abstraction of network stack. Communication between processes, this is right. So inter-process communication. And here in x86, we will have pipe, which will allow us to create a channel which connects two processes. CP, MV, remove, dir, find, make, file. Okay, so who knows the answer to this? Are those system calls, CP, MV, which stands for copy a file, move a file, remove, dir? No, not directly. Those are just applications. Those are processes which implement specific functionality. So we will get to that. And today we will look at a couple of examples of those simple programs, right? But those are not the system calls. And find is actually also a tool which just searches for all files in a directory. So make file, that I'm not sure. Okay, hold on. So what else? So what does this look? You guys actually forgot somehow subconsciously, you forgot the most important category of system calls, and without which nothing will be running. So who can quickly name it? I haven't seen it on the list. Hardware. What is hardware? Exception. Exec, right. So what is this? Exec, so a combination of fork and exec is a couple of system calls which are responsible for starting new processes. You talked about file IO, you talked about memory allocation and deallocation, you talked about inter-process communication, but you didn't name a way to start a new process. So fork and exec are those two which we need, right? Yeah, so privilege change is something different. So we'll talk about it later. So, okay, but pretty much I think at this point you named everything what I wanted. So this is the collection of like categories, and maybe I missed one or two, but I don't immediately see anything. Like you can, like here you can add some F stats, something like that, something like link and unlink a file to create temporary files. Pipe is here. Maybe there will be a dupe which allows you to duplicate a file descriptor, fork exec. So I don't really know many more. So, okay, so that's good. So now we kind of have an intuition for what is it, what is it interface? So kind of file IO, allocation, deallocation of memory, creation of processes, and inter-process communication. Okay, good. So let's start with like step by step. Actually, like here's exactly on the next slide, I have more or less what you named, which is good. So just to give you a hint or a heads up, the thing is that in Unix systems, the system call interface is designed to support shell. And what is shell? Shell is this program, right, which you see on my screen, which has this interface where in which I like it has a command prompt, and I can type a command like ls or like you say cp or mv or find, and this is just a it's not a command which shell implements in most cases. It will just invoke this tool in a file system, right? And this tool will output something on a screen like the list of all the files in a current directory like ls is doing, and then I will get the next command prompt here, right? So back in the days, people were thinking that operating system kernel and the shell are kind of like the two integral parts of the operating system, because shell was the way to interact with the system. It looks a little bit unusual today, right? Because we have GUI, we have touch screens, and we interact with systems with mouse, keyboard, and a collection of GUI primitives, right? And like, I mean, not many of you probably spend a lot of time in the shell. So I spend a fair amount of time in the shell because it's ergonomic for me, meaning my work can be done a little bit faster in a shell in most cases, but it's not always the case. I'm not arguing that it's the best way to do things. But back in the days, that was almost the only way to get work done. Why is that? Because look at this figure, right? So these are the two guys who created this early Unixes, right? Ken Thompson, who's standing, and Dennis Rich is sitting. Ken Thompson sitting, Dennis Rich is standing. They are working together on this PDP-11 machine. So this is their computer, right? But they're using those terminals. And what are those terminals? If you look closely, that's essentially like machines which have a keyboard, and they don't have a screen. They just print out the results of your commands on the screen, right? So it's essentially for them the shell, and the way I see it, like you see it on my screen here, right? So if I like context switch here a couple of times, I do ls. That was like, imagine you type ls and the printer prints you out this, and it's almost like a screen, right? So it's kind of amazing. I do something like cat index HTML, and it prints me back an HTML page on paper, right? But I can interact with the system, right? And so shell was driving the design of this system called interface back then. And surprisingly, these design choices were so powerful that they are still in use today. And there are arguments about it, like whether it was the best way to go. And the answer is probably no. Maybe you can come up with something better, but it still was a very powerful choice. And so today our goal is to kind of understand what these choices were. Okay, later on, people came up with those terminals which had a screen. It's not a computer, right? There is no CPU, nothing like that. It just connects to, like, through a modem, connects to a big expensive machine which is sitting somewhere else remotely, maybe in another room, maybe in another building, maybe like across the state, and multiple users essentially using those terminals to connect to this machine, right? So, but because machine was super expensive, back then the hardware was like in millions, right? And terminals were still affordable, but these are not the machines which were running. So multiple users were sharing this single Unix machine across the network. And suddenly, you know, the choice of abstractions and the choice of shell makes sense, as I say, you know, like those are convenient tools, like ls lists all files in a directory. WC, which stands for word count, with an argument -l, which says count lines, not the words, but lines, will count all the lines in a ls.c file. And there are 85 lines, right? And you can see how you can interact with the system, like with those primitive interfaces when you didn't even have a screen, right? So it seems like a reasonable choice. If I ask you a question, so what is a shell? So does anyone know? You can actually unmute yourself and say terminal. No, okay, terminal. You can say a terminal, but what is a terminal? Interface between user and kernel. Interface to the kernel, user interface, a way for human to interact with OS. I should ask you more questions, read eval print loop, kind of. But what I mean to say is that shell is just a program which starts on the hardware. Essentially, if you remember my picture with a kernel, I'm sorry. Okay, yeah, sorry about it. So if you remember the kernel, shell is just one of the processes which the system starts. It starts them early on boot. And maybe you can think, okay, the first process which starts is something what is called init. And maybe depending on what system you're running, init just immediately starts a shell, and shell connects to the console and essentially prints out the command prompt on the screen, right? Or maybe when the user signs in, logs in, and then for each user we create a shell, right? But what I mean here is that it's just a process. And if you're a little bit like at this point confused about what's going on, so how does this data get on the screen? Remember my demo about Hello World. We kind of agreed that if there is memory, imagine this is all physical memory, there is a specific buffer, there's a specific region of memory, which is called the frame buffer, right? And if the kernel VGA driver, imagine there is a VGA driver in a kernel, if the kernel VGA driver writes some characters into this region, something will show up on the screen like hello, right? How does it happen? The way it works is that there is a piece of hardware which is called a graphical card, right? And this graphical card, through some connection to the CPU, can constantly scan this memory, kind of like read it internally into its own memory here, and then using some microcontrollers either like connect to this digital screen panel, essentially saying, okay, light up those specific dots on the screen, or if it's CRT, then it's a cathode ray tube, then will like modulate the signal in such a way that something will show up on the screen, right? But the point is that this is the graphical card. So this is your graphic card, right? So it constantly reads this region of memory. If the operating system kernel writes something into this frame buffer, it will show up on the screen, which is a different piece of hardware, right? Connected with a cable, something like VGA cable, or maybe it's HDMI or something like that, right? So now what shell is doing, it will be using a system call, and it will be actually using the same read and write system call, read and write. And the operating system, and in a second I will explain how it works. This write system call, by using a specific file descriptor, will connect it to something what is essentially implements a console driver in a kernel, and this console driver will like communicate with a VGA driver and will output something on a screen, right? So just to make sure that there is no mystery how this data, when you write something, how data from shell gets to your screen, right? So right now, of course, we have a bunch of graphical user interfaces on, like we see them because my screen is shared with you, and I can explain how this works as well, but let's do it later. But imagine it's just a black and white screen. This is what I wanted to explain, how this thing gets on the screen. So is this clear? Yes, no? Are there any questions about it? Let me just ask my guys to maybe choose a different room. You guys, it's too loud. Maybe you can move somewhere. Okay, sorry about it. Read and write are the system calls, right? Makes sense to me. Okay, cool. Happy for you. They are system calls. Hold on with me. Bear with me for a sec. We're getting there. Okay, so we got it. Shell is a normal process, but somehow through a file descriptors, it's connected to the console driver. And I haven't explained what file descriptors are. I'll do that in a second, right? And shell interacts with the kernel through system calls. Like you can start other processes by invoking like fork and exec. It can put something on a screen by doing a write. It can read data from keyboard by doing a read, right? So, but other than that, it's just a normal process, right? And in x86, the shell is created right after the kernel boots. So init is created first, and then init immediately creates shell, right? Okay, we got this. And just again, just to demystify what happens here, remember, like it seemed that you were a little bit confused about what happens when you invoke this command, wc -l space ls.c. So this is a command prompt which shell outputs on a screen, right? And then the user types those characters, wc space -l space ls.c, right? And then presses enter. When user presses an enter, this command, the entire thing gets to the shell, right? And the shell parses it. It says, okay, I know that the first argument is the tool which a person wants to invoke, right? And the rest are arguments, and those are actually, the rest are arguments to this. And shell internally, so essentially it will start a new process, which is called WC. WC will start running, will output something on a screen, and shell passes this capability to essentially print something on the screen, right, on the VGA screen to WC temporarily, and we'll be waiting. It will not be printing anything on a screen until WC finishes. Shell will be waiting with a wait system call, which we actually missed on this first screen. And then when the WC is done, the wait returns, and the shell will print out another common prong, right? Just an overview that this is actually a command. This WC, a command which we will eventually invoke with the exec system call. And exec is a way to essentially switch to a different process, right? And I will explain how it works in a second. So this, again, this little detour, is it clear? Are there any questions about it? Okay, so now we are ready to take a look at how this read and write system calls actually work. So everything what is this in this true type font is a system call. Essentially, open is one of the system calls which x86 implements, right? So, and it essentially implements file open. So it takes an argument, a string, which is a file name, and a collection of flags, something like we're opening a file as a in a read-only mode. We're not going to write it. And what open returns is something what is called a file descriptor. So let me explain what these file descriptors are. So for each process, like in this example, it's a cat, right? We invoked it as cat ls. If cat does open inside, like since we pass ls as an argument, right? So cat has to open ls, right? Because it has to read this file to print it out on the screen, right? So what happens is that for each process, operating system kernel maintains a table, which is called the process file descriptor table. File descriptors, like it's a collection of pointers to something what, like we can say a file, but it can be, it may not be just a file. So essentially here the entry is a pointer, and a file descriptor is just a number which says which entry to use. So if in this example we're using entry number 3, this file descriptor will be just number 3, right? So this is clear probably, right? So file descriptor table maintains pointers to file objects, which can be of different types, because behind the file interface, multiple things can hide. For example, a console, like which goes to VGA driver, can hide behind a file. You can read and write into it. The actual files can be there. And also pipes can be there in x86, which will allow you to write into a pipe, and another process will be able to read from a pipe, right? So a process can obtain file descriptors by opening a file, a directory, it can open a device, or by creating a file, or by duplicating an existing file descriptor. Okay, so obviously, okay, if we open the file, so we want to read and write the file, right? So operating system provides two system calls. One is read and one is write. Each of them has takes a file descriptor as an argument. So for example, here, the file descriptor, which was 3, which was returned by open, is passed as an argument here, right? So we're passing the 3 saying, okay, please do the read on this specific file, which I already opened. It also takes a pointer to a buffer in which the read will happen. So essentially the kernel will copy the bytes from disk into this buffer, and also the length of the buffer, right? Which is n. And write is similar, also takes a file descriptor, a buffer, instead of like reading into this buffer, it will read from a buffer and write it to the disk, right? And of course there is a length, right? So this is pretty clear. And ironically or surprisingly, x86, which has the system calls, my system still has the same, right? Essentially on my machine, if I do man read, I will get the same system call, right? So let me just zoom in a little bit here. So the read, the signature is the file descriptor, takes a void pointer to a buffer and a size of a buffer, right? And returns the number of bytes which are read from a file, right? So back then, and Unixes were created like remember Thompson and Dennis Ritchie, right, on this picture, which we just seen a couple of slides ago. They were in 1970s, so it's 50 years ago. They invented this interface. It's still live today, right? Okay, that's pretty surprising. What happens in case like two processes are running in the system? So here, each of them will have a file descriptor table. Those file descriptors can point to the same file. So it's very well possible that the second process will have a pointer to the same file, because two processes can open the same file and read and write into the same file. They have to synchronize somehow to make sure that they are not overriding rights of each other, but maybe they're just appending to a file, to the end of the file. But they also can point to different files. So in this case, this one is wc.c, and this file is ls.c, right? But the file descriptor tables are like identical despite their content, right? So each process will have its own file descriptor table. Again, so console IO, and I kind of already explained it, but the way it works is the following. So there is a convention which says that, and it's just convenient for implementing IO redirection because each program in the system will follow this convention. And the convention is that the file descriptor 0 is a standard input. So by default, if you don't pass additional arguments, the program has to read from 0, from file descriptor 0, right? 1 is a standard output. So essentially, if you do your printf system call, right, and you want to print something on a screen, internally, it will be converted to a write into file descriptor 1, which is the standard output. And if you have an error, then you can write an error to the file descriptor 2, which is a standard error, right? So these three are kind of important, and it will become a little bit more clear why they are important as we go forward today. Okay, so here, for example, how the default console access work, which I was trying to explain before, right? So essentially, when you read from a standard input, this read system call, remember this, goes through an interrupt, but essentially reaches the operating system kernel. It's implemented somewhere over here, like typically the name is sysread. It will carefully validate the arguments, will make sure that the buffer points within the memory of the process and is not pointing within the memory of the kernel, because this way you can read kernel memory and maybe even write into kernel memory. We'll check that the buffer is within the range of the process, because, you know, if you're passing a size which is outside, that's also not okay. Maybe you're trying to read something or write something else, right? But then essentially, the system will configure the first process shell in such a manner that the file descriptor 0 will be pointing to the console device, right? So essentially, init will configure it for this shell. And this console device, as I was saying, will communicate with the VGA driver. And this VGA driver will write something in a specific memory location, which is a frame buffer, and the hardware of the graphical card will be constantly scanning this memory and will read this new hello letters, right, and will output them on the actual screen, right? So okay, we got this hopefully, right? And similar with the write. So essentially, the file descriptor 1 will probably also be pointing, at least in x86, to the console, but the console knows that it's a I forget exactly how it's laid out in x86, but essentially, instead of like writing to VGA, it will be reading when you're reading, it will be reading from the UART, either a keyboard or a serial line driver, depending on how you're connected. If you're physically connected with a keyboard, you will be reading from a keyboard, and if it's a connection over like serial line in a data center, you will be reading from the serial line, right? Okay, so hopefully this becomes clear now. But again, this is an example when instead of a file, the file descriptor is pointing to a device. Device implements the same interface. You can read and write. So essentially, it's kind of a polymorphism, like in a higher level language in which behind an interface, a different implementation can hide. So something similar is happening here, right? So it's read and write is the interface, and what's behind it, what implements this interface, can be slightly different. So it can be in x86, it can be a device like a console, it can be a file, or it can be a pipe. And I think that's it in x86, right? Okay, So let's keep going. So this is the write to the console. Now, okay, remember you got confused about how to implement something like CP or maybe MV or maybe a find. And those things are actually implemented in x86, and you can take a look at the actual source code implementations. Let me just quickly, if I switch here to projects x86 public, and I do something like cat find, a find is not implemented. MV, come on, so MV is not implemented. I was CP will be, no, even CP. No. Then what is implemented? Maybe I was wrong. LS is implemented. Yeah, so maybe those were not implemented in x86, to be honest. But okay, but cat is implemented. And so if you do something like cat.c, you will get the source code. And I have a slightly stripped down version of this source code on the RM is implemented. Yeah. I have the slightly stripped down version of cat on the screen here. And cat does the following. Let me just, I already used it a couple of times. So cat over file. So for example, we take a file which is I don't know, main.c, right? And it outputs it, the content of this file on a screen, right? And you might wonder, okay, so how this tool is built? But this is how it's built. So cat has a tiny buffer of 512 bytes inside, right? And it essentially runs an infinite loop. So what it does, it says, okay, I will start reading from a standard input. Remember, descriptor, file descriptor 0 is a standard input, std in, right? And what it will do, it will pass a buffer and a size of the buffer, and it will read back some number of bytes. And if it reads back 0, it means that, okay, that's done. That's the end of the file, nothing else to read there. And it will break from this loop and exit with an exit system call. However, if it reads something like a negative number, it means that something bad happened. There is an error. And what it will do, it will print something in a standard error descriptor saying that there is a read error in a system, and will exit as well. However, if it reads something between a negative number or higher than a 0, essentially, and between higher than a 0 and a size of this buffer, what happens is that it means that it read some bytes from that file. Maybe it's 10 bytes, maybe it's the whole 512 bytes, right? Because it was asking to read 512 bytes, but maybe it reads less because maybe you are approaching the end of the file, right? And at this point, it will just print out the content of the buffer to the file descriptor 1, because it's a standard output. So that's essentially cat reads from the standard input and writes to the standard output, right? And that's the beauty of it. So, and if write fails, then again, you print out an error and exit. But if write doesn't fail, then everything is fine, right? You got the point. So with those file descriptors and this simple system calls, you already can build useful programs, right? So here, for example, if I want to take a look at the content of a file, I can do ls. I can say, okay, can you cat me something like readme here? I don't have to start a word processor or anything. I have a small toolcat which essentially just outputs this the content of the readme on the screen, right? So that's shouldn't this be echo? So echo is a slightly different thing. So echo does if I say echo hello world, it will just output the same. So echo just echoes the argument. So it doesn't read the file. It will just echo what I say, right? Got it? So slightly different program. Cat is slightly different, right? Cat is like a text editor without editing. You just list what's inside the file, right? Does the cat ls.c and vi ls.c both uses open? Yeah, vi will also use open because vi has to open this file and start editing it, because cat only reads the file, but vi can read and write. Correct, absolutely correct. So cat probably will open a file in a read-only mode, like that's how I would write it, and vi will open it in a read-write mode. So it will output the content of the file on the screen. You change the buffer in memory, and periodically when you save, it will just save it, write it back into a file. So you're absolutely right. Any other questions? Why only 512 in size? Just why more? x86 is a tiny operating system. 512 is good enough, but you can use a larger buffer if you care about performance. or have different other considerations. But for the illustration purposes, 512 is as good as anything else, right? Because it runs in a loop. If a file is a megabyte, it will be reading, it will go through multiple iterations of a loop, right? So it's not as bad as any other choice. LS VI implemented in xv6. What do you mean? LS is implemented, but VI is not. So VI is a much more complicated editor. You can port it to xv6. I'm pretty sure it will run. I mean, if you are careful, but it will take you a while to port, right? So it's not ported right now. Okay. Does cat use fstat to determine a file size at all? Let's take a look quickly at xv6 implementation. I don't think it does. So the code on the screen is essentially, this is what it does. So it opens, if you have an argument, it will open an argv, and then pass this file descriptor to cat. However, here, if the cat itself, so by default, fd will be probably 0. If arguments are less than 1, then we will cat 0, so from standard input, right? And so here we have a loop. Essentially, we just will be looping until the read is greater than 0. So slightly different implementation from the one which I have on the slide, but essentially the same idea. You read something, you're trying to write, right? And you're doing it in a loop. You don't do fstat or anything like that. Meaning every time, yeah, hold on. A good cat would probably use fstat to get the block size of the output fd. Can be, but imagine the file size is gigabytes. You know, allocating that much memory just to scroll through a file may be a wrong design choice. What is the color scheme? Cool. I noticed the inclusion of stat h when you first opened it, so was just wondering. Okay, thank you. Okay, let's keep moving. Okay, we got the cat, right? And we got the kind of the flavor of how these file descriptors and how the read-write interface is supposed to work, right? But okay, let's move to the more interesting stuff. It's essentially the mechanisms which allow us to create new processes, right? Okay, the way it works is that Unix uses a combination of 2 system calls for creating new processes. It's a combination of fork and exec. They feel a little bit unusual, but as we go forward, I hope you will understand the logic behind them. So let's take a look at fork first. Fork is a very mysterious system call. So essentially what fork is doing, if some program invokes fork like right here, what happens is that the fork system call drops into the kernel, and in response to the system call, the kernel creates an absolutely identical process. It has the identical memory, so every bit in this one and in this one will be the same, right? The only difference that inside the parent, it returns a process ID of a child. So if this one has a PID equals to 32, this is what will be returned to the parent which invokes the fork, right? So the logic, the terminology here is that the program which invoked fork is called the parent, and the process which got created is called a child, right? And the parent maybe had a PID of, I don't know, 17, for example, because it was created a while ago. And inside the child, the result, the return from the fork returns 0, right? So it's essentially a difference of one register in which this return code is returned. So EAX register, which will contain the return value from a function, which will be placed in EAX. Here will be 32 and here will be 0. But other than that, they're completely identical. Okay, you might wonder, how does it help us to create a process, right? You just clone the same process. It doesn't seem to make much sense. Okay, let me keep going for a second. So just again, a little bit of an overview, again, some illustrative example which shows how fork works. So here we invoke the fork return a PID. Inside the parent, you can check that PID is greater than 0, right? Because it can be less than 0. For example, here, it means that there was an error. Maybe the system ran out of memory and you cannot clone a process because there is simply no memory to allocate memory for a new process, right? But if it's greater than 0, you can say, okay, I'm inside the parent because I know that I got the result, which is greater than 0. And you can print out, I'm a parent with a child, which is has a following PID, right? Then you can waiting for the child to finish. And then you can print, okay, child with this PID is already done. Inside the child, you check if the PID is 0, right? So it's the PID which is returned from the call. And you say, look, I'm a child. So you can distinguish parent and child with just by simply looking at this return code, right? And you can exit here. So pretty much simple. You can say, okay, cool. But again, as I said, fork, not really clear. How does it help you to create a process? So fork is used in a combination with another system code, which is called an exec. Exec is a slightly weird system code. What it does, it replaces the memory of a process with a completely new binary. So for example, in this example, imagine you wrote your own main C function and you call this binary maybe foo bar. So it's a process which is called foo. Inside foo, you create specific arguments which allow you to invoke exec here, right? And you say, please replace my memory with bin echo. And essentially, if you invoke exec and exec goes through, it doesn't return an error, you will never reach this line because the memory of a process will be completely replaced with bin echo, and bin echo will start running. So let me illustrate it with this example. So imagine you did a fork inside from a shell, for example. Inside the parent, you get a process ID, PID. So maybe you're going to be waiting for this PID, maybe you're going to be doing something else. But inside the child, where you're getting 0 as a result of return from a fork, right? You're doing exact bin W count. And the entire memory of this shell gets erased and gets replaced with WC, right? Is this clear? Because it's a little unusual. It's not how you would imagine creation of a process will look, right? Because one would say, okay, why can't we do something like implement a create system call, which takes an argument to bin WC, and as a result of this create, maybe you return a PID or something, this WC starts running, right, in a system. Why do we first do a fork and then replace memory of a fork with exec, right? Does anyone know the answer? Safety. How does safety work here? Process isolation. Well, create can also drop into the kernel. Create, like the kernel will do something and will pop up WC right away. So no need to fork. Keep track of new process. Okay, guys. So the actual reason is the idea. It helps to implement IO redirection, right? Let me explain what it means. So IO redirection is a powerful idea, which you might or might not heard of, but let me just illustrate it. Okay, imagine we're looking at a couple of motivating examples. Imagine you want to do something like this. So normally WC sends its output to the console, right? You show it up, you see it on the screen. So if we do something like this, if we do something WC main.c, for example, we'll get that it has 3,580 characters, 491 words in 134 lines, right? So if we invoke with -l, we'll get 134 lines, right? So it outputs on the shell. But imagine I want to redirect the output into a file, right? I want to write this output into a file. And you say, okay, sure, I can add an additional argument, kind of like it will take an additional -o, saying, please use this file as an output. And that works, right? So you can say that, but this is a little bit ugly. And you can imagine that maybe shell can somehow support this functionality, which allows you to redirect output of one program somewhere else. And shell does. So instead of doing this trick with -o, for any program which may or may not support this -o argument, shell supports this symbol, which redirects output of this program, P1, into this destination, right? So if I do, for example, if I do the same experiment here, but instead of doing this, I say foo, the output, like see, nothing showed up on the screen. Everything what was printed by WC went into foo, right? And someone would say, can I do, no, echo just takes a literal argument, right? So I can read it from a file with cat, right? I can do that, but really output went into a file. So this is kind of like powerful, but you may or may not be impressed, but I will impress you a little bit more in a second. Let's just take a look at other things. So first you can redirect output with this symbol, right? And we can type something like this. So please redirect output into foobar, or please redirect output of cat into another file. So this way you can actually copy a file. So because cat reads ls.c and writes, in this example, writes into another file. So this is essentially a copy, right? You can also, shell supports also redirection of an input, right? So you can say, instead of like providing an argument to WC, please take ls.c as an input, or please take ls.c as an input to cat. And of course, you can redirect both. So in this example, we are redirecting an input and redirecting an output at the same time. And what shell is doing is this is just, it does parsing, and if it finds those symbols, it reacts appropriately and will somehow replaces the standard input and the standard output for the program in such a manner that standard input in this example will be connected not to the console, but instead will be connected to ls.c, right? Okay, you might think of it like, why is it so useful, right? So let me again illustrate how everything works here. So for example, here, when we're redirecting a standard input and a standard output, now instead of being connected to a console, right? Like the shell had them, sorry, they are connected to a file, right? So both of these arrows point to a file. So this program, which is running here, I don't know what name it is, but it can be like, it can read from this file. When it does read from 0, it will be reading from this file. And when it does write into 1, it will be writing into this file, right? Maybe it will be different files if you want, right? The question is, why are we doing this? So first of all, let's observe this powerful design choice. So file descriptors, it's like this language polymorphism, which I was mentioning earlier. File descriptors don't have to point only to files. They can point to a console, a pipe, or a file. And suddenly your program, no matter what you like, you wrote it once. And if it writes something to standard output, it can write either to a console, or it can write to a file, or it can write into a pipe, depending on like how you run this program, how the shell runs it, right? Okay, still maybe not super convincing, but again, like just to take a look, like cat, which always reads from 0, writes into 1. If someone does cat redirect input and ls.c, instead of like reading from a console, if I just run the cat on a console, if I run cat like that, it will be reading from here. So it will be working like echo. I will say hello, and it will print me back hello. I will say hi, it will say me hi again, right? Right, so it reads and writes from the standard input because I didn't pass any arguments, right? But if the shell, if you invoke it with the shell in such a manner that you say, cool, I want to do something like cat from ls.c, then it will be reading from cat.c. And if you want to write into foo, it will write into foo, and then you can just essentially take a look at what's inside foo. It's ls.c, right? Okay. Still, as I said, maybe you're still not entirely convinced that it's like a killer feature which is so useful that you want to use it. Let me give you a motivating example number 2. Imagine you want to do the following. You want to see how many strings inside ls.c contain the substring main, which is a little bit unusual, so it's a little bit artificial. But imagine maybe you have a database of users or a file with users, and you want to see all entries in which name of the user is Anton, for example. You want to count how many Antons, or even to make it more realistic, if the city in which user lives is Irvine, you want to count how many people live in Irvine. And you say, okay, look, normally I need a relational database for that, so to build a query, but you can do that with those simple tools inside shell. Let me show you. So imagine you have another tool, which we will call grep. It's a real tool. Grep filters strings which match a pattern. So essentially, if the string doesn't contain the main pattern, grep just throws it away. If it contains main, it will output it back on the screen. So for example, if we invoke grep saying, okay, filter everything that contains main. Inside ls file, it will output only a single string, right? Because there is only one string which contains this main substring, right? And grep will output it. Now you can write it differently. You can say, well, grep redirect input to ls.c, right? And it will again output just one string. Now you have to make the following observation. You have two tools, right? You have grep, which filters strings, and you have wc, which can count lines. So now you say, if you have this user file, right, which contains people who live in Irvine, if you first filter them with grep, you will only have strings which contain Irvine, right? That's Irvine. And then if you have wc minus l, you can count them and get the number 3, right? So the question is, can you combine them with IO redirection? And shell supports a notion of a pipe, so which allows you to essentially connect the output of this first program to something what is called a pipe, and connect it to an input of this program, of the second program, right? A pipe does redirection, meaning that everything what is output by ls becomes an input to the grep main, right? And naturally, this becomes this powerful idea, right? You can now connect multiple simple tools together, right? This is exactly what we wanted, right? So cat's output is connected to grep's input, right? So grep filters all the lines which match a specific criteria, ones that have main. So if you put another pipe here and you say, well, wc minus l, this will output you the number which you're looking for, right? In case of this, in this specific example, the output will be 1 because there is only one line inside ls.c which contains the main substring, right? That's pretty powerful. Like, look, especially back in the days, you didn't have powerful word processors or Excel spreadsheets, but with those tools like cat, grep, wc, you suddenly can like get answers about specific questions which you care about, right? So it's not a relational database, but it gets there, so you can build queries, right? Okay, so I mentioned pipe. Let's take a look at what pipe is. So pipe is also a system call which creates a specific object in a kernel, right? So pipe contains a region of memory inside the kernel, let's say 512 bytes again. So it's a kernel buffer, which is exposed as a couple of file descriptors. So there will be a pipe object in a kernel pipe, like a data structure, which will contain a pointer to this buffer. And when someone does a read of a file descriptor, which goes through a file descriptor table, but which points to this pipe, this read really will return data from this pipe. If there is no data, it will wait for data to appear. If there is at least someone else in a system who still has a pointer to the right end of the pipe. So pipe will have two ends, a read end and a write end. And if there is another process, or maybe the same process, which has the right end of the file of the pipe open, which means that in the future it's possible that data will appear, this read will block and will be waiting, right, for this read to appear. But if there are some bytes, like already maybe 16 bytes, and you're trying to read 8, it will happily read this 8 bytes and will return to you, right? So pipe will allow two processes to send bits or streams of information from one to another, right? So okay, let's take a look at this diagram here. So it's essentially the same drawing. So here's the pipe object. It will be containing a buffer, and when someone does a write, so there is a pointer to a buffer which will contain information here, right? When we do this write into a third file descriptor, the third file descriptor is connected to a pipe. So the operating system will reach out to this buffer and essentially copy this buffer into the intermediate buffer of a pipe inside the kernel, right? If you run out of space here, you can only copy maybe instead of like all the, maybe you said 1024 bytes. I think you will be only able to copy 512, and then the write will block as waiting for someone to read some data from a pipe and clear up some space in the buffer. So here the read comes in, again, a pointer to a buffer here with some specific size. It goes to a file descriptor, is pointing to the read end of the pipe. So this is the right hand, this is the read end of the pipe. And those bytes which are already here inside the pipe are copied by the operating system in the memory of another process, right? Is this idea clear? Let me stop here for questions. Any questions? You can unmute yourself and ask or ask in chat. All good, you got the pipe? Is it a loop buffer? What you probably mean to say, is it is it a circular buffer? Yeah, it's a circular ring buffer, meaning that I will explain organization of the pipe inside x86 towards the end of the class when we will be talking about synchronization. But the idea is that, yeah, as you move forward, those bits gets cleared and there is like tail and head pointers, and you can like circle around, right? If you understand what it is, you probably got the answer. So anyone else? Okay, so let's keep going then forward. Okay, pipes allow us to connect programs, right? The output of one program to the input of another. So now we say, look, one program P1 somehow has this connection to another program P2, right? And shell does it for us. So for example, if we do ls, whatever we did there, cat ls.c pipe into a grep, filtering from main. So this will be your grep, this will be your cat, right? And the cat will be reading a file which is ls.c, will be writing string by string, will be writing this file string by string into a pipe. Grep will be reading string by string from a pipe and will be matching it with a main. If something matches, then it will output it on the console, right? Or on its standard output, which is in this example connected to the console. If read is from the file descriptor 4, how is it seeing the pipe buffer? It's this, okay, so this is a little bit of a miscommunication here. Those numbers don't have to match. This can be 3, and inside another process, this can be 55, for example. The point is that this entry 55 inside the kernel points to the same pipe object, because pipe is a data structure, like a normal C data structure, and you have a pointer. And when you say read from 55, the kernel will look into this file descriptor table, will find this pointer, will get this object, will understand that, okay, by the way, it's a pipe, right? And then it will start using pipe API to read from a pipe. Is that clear? Matt, yes? Okay, hopefully it's clear. If anything, we can take it offline and come back to this.
Yeah,
okay.
That's clear. Thank you.
Okay, so what pipes, as I was saying, they allow this composability. Suddenly you can build queries. You can say, look, cat ls grep main w count wc minus l, and the output is 1. But it gets even better because you can easily switch from main to an A, saying, okay, please filter me all lines inside cat ls.c, which actually contain not only ls.c grep main. So here, of course, we'll have only one line, which is wc minus l. But if we say, look, I want to count all lines which contain just A, you will have 33 lines because grep filters all the lines which contain A, right? So this is cool, right? So this example, you say, look, this suddenly becomes composable. And this interface with IO redirection suddenly makes a lot of sense. So out of small tools, you can build something useful. And it's much, especially back in the days when you didn't have any graphical interface, but arguably even today, this graphical interface is a horrible choice, right, for everyone, right? So you're searching for tests. If you want to switch, you have to AA. You say, well, where I'm searching here, I can compose and I can search through the directories. I can enumerate all files in the directory and then pipe them into this pipeline, saying, okay, please search in those files. So it's all clear on Unix, right? On Windows, you have to like check a bunch of check boxes just to like even perform this simple thing. So even in terms of ergonomics, the choice of those pipes feels like a good idea, right? because not even like disregarding the fact that, okay, back then they didn't have a graphical user interface with those checkboxes and mouses, right? And Windows for quite a while they didn't have. I don't think maybe they now do have pipes, and they kind of copied Unix eventually, but this is the power of Unix design choices is still lives with us. Okay, cool. But this, remember, it was just kind of like a couple of motivating examples, and we're just coming back to the main reason why do we need fork and exec, right? And it's related to the fact that fork and exec are responsible for implementing this IO redirection, right? So let's take a look at how we can actually build IO redirection, right? So imagine the shell which processes this string. So essentially it says, okay, look, user parses the string. I have to parse it. I identify that there are a couple of pipes, and I get it that there's three different programs like P1, P2, and P3 need to be started. I have to create, in the end, the shell has to create P1, which is cat, connect it to a pipe, right? Connect this first pipe to the input of grab, connect the output of grab to another pipe, right? And connect it to WC. So WC is still connected to the standard std out, and cat in this example takes input from, it's still connected to std in, but it will be, since we're passing an argument, it will read from ls.c, right? The question, like, imagine you're building a shell, and it will be one of your homework assignments, assignment number 2. The question is like, how can you build this pipeline, right? The question is like, do you have enough system calls to do that? And it turns out that you do. That's the beauty of it. Okay, so how is it done? So imagine you have a shell. So when you invoke a fork, you will get an identical copy of the shell, right? A child. But this child can do something. And for example, the one convention which fork is preserving is that it copies the file descriptor table of a parent to the child, meaning that if parent had file descriptor 3 pointing to a file, the child will have the same file descriptor 3 pointing to the same file, right? Right after the fork. So, however, you can actually manipulate file descriptors. You can close them. So for example, if you want to replace standard input, so it's a file descriptor 0, you can say close file descriptor 0. You can pass 0 here and say close it. And what it means is that your file descriptors table, which might have some additional entries and used to have an entry here, but here this one becomes null because you closed it, right? Right? And the convention which Unix implements is that the next open file descriptor, so if you say open at this point, if you say open, the next file descriptor will be the file descriptor with the smallest number, meaning that the operating system will start scanning from 0. And in this specific example, 0 is null. So it will say, okay, I will return you file descriptor 0 because it's the smallest one, which is unoccupied. If you had a file descriptor which looks something like this one is taking, this one is taking, this one is empty, this one is not, isn't taken, this one is taken, this one is taken, you say open and some foo, some flags, which file descriptor number you will get as an answer as a result of this open system call. Who can tell me? They start from 0. Who can tell? Remember the convention. So am I like, did I lose the chat? I can't even read on the chat anymore. Ah, okay, got it. Scroll up. Sorry, guys. Thank you to Zoom. And I don't know how it looks on Windows, and on Unix it looks horrible. Damn. Okay, so how can I get to the last message? Come on. Ah, this way. I have to change the focus. No, I cannot. So can someone? They can't be the same number, right? They can. So annoying. Okay, let me close it again. Maybe I'll open it. And we only have 2 minutes left. Let me try again here. Trying to get back to the chat. Good luck to me, probably it will not happen today. Come on, people. No. I have participants, but I don't have chat. Okay, so if we don't have an answer, I hope we do, but I don't see it. So can someone unmute and say what the file descriptor number will get?
I'm just gonna say it's 2.
2, exactly. 0, 1, and 2, because 2 is the smallest one, which is unoccupied. So we'll get 2 here, right? That's the convention. And I mean, it looks a little bit artificial. So you say, why would I need this convention? But the convention is following, that you can control the number of the next file descriptor, which will be opened, right? So this is a specific example. Look, if you shall, as a parent, forked the child, after the child was forked, the 0 was pointing to the console, right? However, shell can say, look, I will close 0. So this 0 will become the first unoccupied file descriptor. If I open ls.c, because here we want to redirect input from, instead of like using standard input, we want to redirect input to a file, right? Read a file instead. The shell can open ls.c, right? And the 0 will start pointing, instead of pointing to a console, it now points to ls.c, right? This is how shell, after invoking fork, shell can implement IO redirection, right? Because it has a window of time. Remember, the end goal here to invoke exec and start executing cat. And it will happen in the next line, essentially, right here. But this window of time between fork and exec allows the shell, gives the shell control over the child process, over the future child process, and allows the shell to redirect file descriptors. Is that clear how it works? And at this point, we are running out of time. So let me stop here and I will take some final questions and then we will continue on Thursday, right? Is it? Or we will continue when? Is it next week really? Yeah, next week, Monday. Oh my gosh. Yeah, we're a little behind. Okay, so tell me, any questions?
I have one.
Yeah, go ahead.
If you are reading and writing the same file, does the file descriptor has to be the same number?
No, that's the beauty. You can open file twice if you want. It doesn't have to be.
Got it. Thank you.
So normally you wouldn't do this because it will probably confuse you even more than help you, right? But it's technically it's possible. Let me open chat here. Finally, I'm back to chat. So you were answering 222. One was saying 3. Sorry guys. Yeah, I lost it horrible just because of how Zoom works in Linux. And I prefer to teach from Linux just because I can give those examples from the command line. Otherwise, probably it would be much smoother. It's better on Boss. I have used Boss. Okay, you made my life a little bit better. Okay, so let me stop here and we will continue from this point next Monday. So thank you and I wish you a good weekend. See you guys then next week.